Let's see here. We'll go over image formation by refraction first. Let's say that we've got a fish under the surface of water. So here's the water surface. We've got air above and water down below. And if we have a fish down here, sorry, it's not a particularly good fish, but there. Now the light ray coming up from this. Let's take a light ray that's going up and to the left. Remember, when it hits the boundary with the air, the index of refraction of water is about 1.33, while that for the air is about 1.00. So, going into a material with a lower index of refraction, the light ray bends away from normal. Now, if we're looking at it, if we're here, and we see this light ray, so there's our eye, again, assumes that the light ray is traced back in a straight line, and so it sees the fish appear to be here. This is, again, a virtual image. And this is the object. Again, the virtual image means that the image means where it appears to be. Virtual means that the light rays don't actually come through that point, or they don't emanate from it. Now, what about... This tells us that it appears to be higher up. It doesn't really appear to be closer to us. In this case, and I will also note, the same holds true for the bottom of the creek. The bottom of the creek will appear to be higher up, and the water will appear to be more shallow until you start stepping into it and you look more or less straight down. But even then, what about if we're right down on top of a fish? So here's the surface of the water, here's the fish, okay. Light rays, one that goes straight up, well, let's see. It's going to bend away from the normal, but if its angle is 0 with respect to the normal, the outgoing ray has an angle of 0. So one that's perpendicular to the surface, normal to the surface, will remain normal to the surface, even on the other side. And I should draw the blue water there. Okay, but now, light rays that go off a bit to the side here bend away from the normal. Light rays that go off a bit to this side bend away from the normal there. And what happens is that an eye that's gathering those light rays together there sees the fish appear to be, with the virtual image, appears to be right there. So even when you're looking at it from straight on, the fact that you always have some diverging rays there from an extended object, or your eye will, for that matter, your eye gathers a range of rays. That would be a pretty big eye, but I'm exaggerating the angles there. It will always see those converging to a point, appearing to converge from a point, emerge from a point that's much closer to it. All right. That's where the phrase still water comes from. While it's metaphorical, it's talking about the appearance of the bottom of a creek appearing to be much shallower than it really is. All right, now let's talk about the dispersion of color. This is a nice topic, and I've got some demonstration material. Flashlight out from my phone. I'll be using that to illuminate this. So far, I've been showing the index of refraction for a given material. I've been treating it as if that's the index of refraction, no matter what the wavelength of light we're using is, but that's not the case. There generally is a change of the index of refraction as a function of wavelength. So, for example, if I plot index of refraction n as a function of wavelength lambda, let's put what the range of visible colors is. Now, this is something that's useful to know as well. The human eye can see colors of light that range from about 380 nanometers on the far edge of the violet down to about 750 nanometers on the long end on the red. So let me mark this from 400. This will all be in nanometers. 500, 600, 700, and then 750 will be out here. So red is from about 650 to 750 nanometers. Orange, you're dealing a little on the long side of 600. Yellow, you're slightly on the short side of 600. Green is from around 500 to 580 nanometers. Blue is on the short side of 500. Just write blue here. Now, it's hard for me to look up the wavelengths for indigo. We traditionally do break it up, the Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, to take place in between the narrow range of blue and the somewhat wider range of violet there. But the places that we're looking at just lumped it all together into violet. So, violet is from about 380 to maybe 425 or so nanometers. Of course, beyond the violet, above the violet would be ultraviolet, and below the red would be infrared, infra meaning below. All right, so there are the visible colors of light. Now, for glass, a typical function of index of refraction versus wavelength for glass goes from around 1.54. Make sure that's in the field of view of the camera here. Okay. Down to about 1.51. So when you take these off in the middle, and the index of refraction in these cases is higher at the violet end and lower at the red end. Something like this. It's not a straight line. Let me make sure that that's clearly curved. There. So that's n as a function of wavelength. That's a little curly arrow pointing to it. All right, lower index of refraction at the red end means that red light is bent, refracted less. The index of refraction tells you how much, the bigger the change in the index of refraction from one material to another, the larger the bending will be at a given incident angle. Violet light is refracted more, red light is refracted less. Okay, with that in mind then, let's take a look at a prism. So if we've got a prism with a triangular cross-section here, made out of glass, let's have let's see, what did Sir Isaac Newton figure out? Before Newton's time, he lived in the 16 and early 1700s. Before Newton's time, people had noticed that sharp-edged pieces of glass tended to make colors when you shine white light on them, but they thought that the glass was adding color to the white light, being colorless. Newton was the one who figured out that these pieces of glass, prisms and so on, were actually separating colors that were already there. One thing that he showed is, well, taking the prism. He did these good experiments with a prism. You shine white light through. Now I'm going to show blue and red because I've got those here. Let's shine it through slightly up and to the right. There. And a red beam right next to it. Now, Snell's law. We measure the angle of incidence away from the normal line. Now, N1 sine theta 1 equals N2 sine theta 2. Snell's law in action. There's theta 1. So what's theta 2 going to be? Well, if you've got something like 1 for air out here and something close to 1.5 in glass on the inside, that means it's going to bend towards the normal. It's going to a larger index of refraction, it must bend towards the normal. But you see here that for blue light, glass has a larger index of refraction, so it's bent at a larger angle. The angle, it's bent closer to the normal, that's how I should say it. Whereas the red light is bent less. Okay. Now, when they get here, you see this side of the prism is at a different angle. So the normal lines don't line up with the originals. So here, now, here you're starting in close to the normal line, you must bend away from it. And the blue over here comes in, it's starting a bit farther away from the normal line, it has to bend even farther away from it. That means that it separates out the colors well. They exit, already separated, disperse a bit, and then angling away at different angles. Okay, so always keep in mind what the prism did. The blue is bent more, the red is bent less. The red has very small changes in direction as it goes through, relatively small. Okay, that brings us in to the idea of how a rainbow works. For a rainbow, let's take a single drop of water, a raindrop, fall into the air, and we get the same kind of thing going on. If we've got white light coming in, so let's take it moving horizontally and hitting at this upper edge of the raindrop. I'll take the red first. Okay, so there's the red, and let's go and draw the blue there. Okay. Now the normal line for a sphere, let's assume that the raindrop is a sphere to make it simple. The normal line will always point straight to the center. There. So now the red one is bent less, but it's still bent towards the normal. So it comes over like that. The blue one is bent more towards the normal. There. Wow, look here. Now when they get to this side, they're inside the water and the air is outside. So you do get, let's see here. There we go. Now, you do get a transmitted ray at both of these points. We're only going to be interested in the reflected ray that stays inside. This is not total internal reflection. It could be at some angles then, but we're not talking about it here. So, angle of incidence equals angle of reflection. I measure that angle, comes out at the same angle here. And that one, let's see, that was coming in at a narrower angle. Right, it was bent closer to the side here, so it comes out like this. Now notice, they cross over. That's a key thing. They cross over, and when they get to here, okay, they're going from water into air, so they're bent away from the normal. That means this one is bent out this way, and the red one is bent that way. Sorry for the screech. Okay, see how again how they cross over at this point. Now, the angle that they're bent through, if you compare the incoming direction to the outgoing, and what that angle is there, right? You trace a straight line from the incoming ray and then the outgoing ray and see where they would intersect. What is that angle? The red light is refracted at around 42.5 degrees with respect to the incoming ray, and the blue light exits at about 40.8 degrees. I should say the violet, not the blue. 40.8 degrees. So how does this work in practice? Let's say you're standing on the ground. On the earth here, I'm going to erase some of this. The sun is low on the horizon, or moderately low in the sky. You're standing here. Now, take a line from the sun to your head. This is not the line of the light rays. This is just, we need to make this line. It goes down to the earth and would continue there. This is called the anti-solar point, the point directly away from the sun. Okay. The rainbow is centered on that line connecting the sun to your eyes and going away from it. Now, because the red light is bent through a larger angle, then when you see red from one of the raindrops, it's higher in the sky than the blue light is, because that's at a smaller angle, and so those are the ones that are lower in the sky. So what we see is a red bow here, like that. And then inside that, you'll see the blue light, or the violet, but I'm just coloring these two colors because they've got chalk. And then you've got all the other colors in between there. Now, so you're going to see these standing out like that, surrounding a point opposite the sun. So as the sun sets, the rainbow will appear to rise. And if the sun is very high in the sky, then the rainbow will be lower down, and you've got less of a chance of seeing it. Because you've got to be looking through raindrops that are illuminated by the sun. So you've got to have a path that includes those. That's why you only see them under certain conditions. All right. Now, what about a double rainbow? In a double rainbow, it's when you've got an extra reflection in here. So for raindrops at certain, where the sunlight is coming in at certain angles, you'll get two reflections and then the refraction outside. It's weaker because you're transmitting some of this light with every reflection. Some of it's transmitted through. So the amount that's reflected internally is less, and so the double rainbow is fainter, noticeably fainter. On the other hand, though, because it's got that extra reflection, then they switch the order again. And so in a double rainbow, you have the, let's see, the blue, or the violet, I should say, is on the outside edge, and the red is on the inside. And it surrounds the brighter main bow. There are all kinds of other effects that can be seen with these things that I don't have time to go into, unfortunately. But it's really an interesting application of this. And I recommend that you take a look at a book. It costs about $16. It's one of the cheap Dover, inexpensive Dover reprints. Dover makes good quality science books that are inexpensive and well made. And this is by Minert, who was, he was Dutch, lived in the mid-20th century. The nature of light and color, he used the British spelling, in the open air. Like I said, you can get it for $16, something like that, and it is well worth reading. He's got terrific drawings and sketches in that, and some photographs too, and explanations of how these things work. All kinds of atmospheric effects, optical effects, and so on like that. My freshman physics professor had strongly recommended us to get this book, and I'm very glad that I had. So I've had my copy for 20-something years now, 25 years. Okay, so that gets us through rainbows there. Now another application is you can make, let's take a look at color filters. I'm going to leave this chart up here for a moment. So, if you have a filter and you shine light through and it looks red, why is that? So if you've got white light coming in to this, and but only red light coming out, see what's happening is it is opaque at every wavelength of light except the red wavelengths. It's absorbing all of the other wavelengths of light and letting through only the red. On the other hand, if you have a piece of material that is reflecting, so you shine white light on it, and what bounces off is red. If you see it look red by just reflecting, it's absorbing all the other colors and it's reflecting only red. So transmitting, reflecting. And of course, some materials will do the same for both. Okay. So that's one way of making a color filter. You can select only the wavelengths of light you want. You can make them where they are broadband, meaning a wide range of wavelengths, or narrowband, where they only have a very few wavelengths. Now, there's another kind of filter. Oh, and by the way, you can also make what are called interference filters, where you set up a thin film. Actually, we've mentioned about thin films before, so that only certain wavelengths of light can fit between the two barriers in the film, and it passes only those, absorbing everything else. All right, now, with this thing on color dispersion, with the varying wavelengths, varying index of refraction as a function of wavelength. If this is how a typical kind of glass behaves, what about if I look at other materials, like an oil? Some kinds of oil, let me see, I should put the glass, I should put that in blue. And I'll put the oil in white. Some kinds of oil have a steeper curve here. So what happens then if we've got glass and oil in contact with each other? and look at this point right here. Now, at this point where those curves cross, at this wavelength, these two substances have the same index of refraction. If you go from one substance to another that has the same index of refraction, take a look at Snell's law. All right, if N1 equals N2, so I'll just say N1 sine theta 1 equals N1 sine theta 1, sine theta 2. Those cancel out. The sines of the angles are the same, and therefore, by taking the arc sine function, the angles are the same. There is no bending of the light. There's no refraction at that surface where you go from one material into the other. It goes straight through, no matter what angle it's coming in at. You can use this fact to build a really intriguing color filter called the Christiansen filter. So you take glass and you pick a certain kind of oil that has the same index of refraction as the glass at the wavelength you want. Actually, you use crushed glass. Now, you put it in a jar. And then you put the glass in the jar, and you pour the oil over it, and it fills in the gaps here. Now, for any wavelength of light, other than the one where the curves match, let's say you've got very violet light coming through. Now, just as an example, here is a Christiansen filter I built. I haven't put the oil in it. Now, notice I've got crushed glass, not terribly crushed, but I didn't want to get glass powder all over my fingers because it's hard to wash off, and then you wind up eating, you get it in, and just it tears up your intestines. All right, so there's the glass. Now, why does this look white? It's because the white light coming through, every surface of glass it hits, when it goes from glass to air to glass to air and so on, it's at a different angle, and so that it keeps refracting, bending from one direction to another. This winds up scattering the white light fairly evenly in all directions then. You see, it's fairly evenly illuminated there. So this is why ground up powders of glass and such, or a rough surface of glass, diffuse the light very well. Now, so the same is true then for a wavelength of light where the indices of the oil and the glass are different. When it goes from oil to glass, it bends. From glass to oil, it bends. And because these are crushed pieces, it goes off in all different directions. I should just draw straight lines. So but for the wavelength of light where they have the same index of refraction, it just goes straight through. And you get a nice even beam coming out. So, let's take a look then. I've got my flashlight on the phone here. There. So you can see that this is dispersing the light fairly evenly in all directions. There are little colored fringes if you looked up very close. Now, okay. Now, I've got methyl benzoate from a chemical supply, or actually from the chemistry lab here. As I pour this in, all right, just enough to cover up the glass. This has got a peppermint kind of wintergreen smell, actually. I'll have to get this up closer. Now you may be able to see that the light that's passed is on the, there are actually strong bands of color here. It's a little harder to tell, but it's a kind of a greenish light that's able to go straight through. And other wavelengths are dispersed, scattered to the left and the right. I'm not sure if the bands of color are really making it through in this camera. Let's see. Not terribly well. Okay. Anyway, it does do it. I should also show them, not sure how much this will do it. So for the green here, this is scattered quite a bit, as you see as I move from one spot to another. It's always hitting a surface that it refracts off of. And the same for the red. The Christiansen filter has some limitations. The red isn't quite as bad. Maybe that's it there. Maybe it's the red that goes on straight on through. The green is definitely broadly dispersed. And the red, yeah, you can see straight through on the red. Okay, I forgot what wavelength it passed. All right. Now, a nice thing about the Christiansen filter, though, is that the wavelength at which these curves cross changes with the temperature. So as you heat this up, then this intersecting point will change to, I forget if it warms up and it changes to the red end or if it goes down to the violet end. But it's a temperature sensitive one. This means that it would be tough to use in direct sunlight because the strong sunlight would warm the filter itself and change its index of refraction. Okay, last thing. While we're on the idea of scattering then, is why is the sky blue? Well, let's see. Before I even draw the Earth here, if we've got air molecules there, now it turns out that there's a process called scattering, and there are several different kinds of scattering. What happens is when a light ray hits a particle, it is re-radiated in certain directions. It could be fairly evenly in all directions, depending on the size of the particle, or it could be more strongly in one way or another. We'll deal with the kind of scattering called Rayleigh scattering. Which is appropriate for the size of particles we're dealing with in the atmosphere. Now, Rayleigh scattering says that the intensity of the scattered light, now scattered means diverted away from its original direction. Unscattered is what passes straight on through. So if you set up a hammer here at angles away from the original angle, you would be measuring the intensity of the scattered light. So for Rayleigh scattering, the intensity of the scattered light is proportional to wavelength to the -4 power. So the shorter the wavelength, this means it's inversely proportional to wavelength to the 4th. So the shorter the wavelength, the greater the scattering is going to be, the more it's scattered away from its original direction. That means red light tends to pass on through with very little scattering, while blue light, I'm going to speak in terms of red and blue as the opposite ends of the spectrum. we would of course look at this and say red and violet, and for whatever reasons, maybe the fact that it's one syllable versus three, we astronomers tend to just say the blue end of the spectrum to mean the short wavelength there. Regardless, the blue or the violet end is scattered more, like that. So, this means, let's say the sun is over here, sending out all the colors of the rainbow, and in particular red and blue light. Now, if you are standing here, let's say, with the sunlight coming down on here, and in all directions into the air, if you're not looking straight at the sun, what color of light do you see? Now, if we had no atmosphere, the sky would be black, aside from looking straight at the sun or looking at stars. But as it is, standing here, if we look at the sun, we see the sun's color. If we look at the sky in a different direction, what colors do we see? Well, the only color that's strongly scattered is the blue or short wavelength into the spectrum. Violet, indigo, blue, and so on. But as you get onto longer wavelengths, less and less of it is scattered. Now, the wavelength that's emitted by the sun peaks, the biggest output of light is near the middle of our visible range, yellow, yellowish green, somewhere there, which is not surprising. Our eyes are adapted for sunlight. So if you get onto the violet end of the spectrum, there's actually less light emitted in the first place. If you get closer to blue, to green, to yellow, there's more light emitted. If you go on to orange and red, there's less again. So the reason the sky is blue is that it's more strongly scattered than the longer wavelength colors, but also there's still plenty of blue in sunlight. If you try looking at violet, violet's even more scattered, but there's less of it to begin with. Now, what about the red? What about red sunsets? When we're here now, the sun is low in the horizon. I've just moved the Earth apparently. You notice, well, the Earth's going to spin around. So if we're here, looking in the direction of the sun at sunrise and sunset, the atmosphere is only about 50 miles thick. If the sun's high in the sky, there's only this much, 50 miles worth of atmosphere to scatter the light around. And so looking towards the sun, you see the sun looking, what color does it look? Does it look yellow? And that's actually kind of a fringe around it that's scattered yellow light. The sun is actually white looking to our eyes, not that you should be staring at the sun. And the reason you know that it's white looking is that if you take a piece of white paper that reflects all colors of the light evenly, and hold it out in direct sunlight, what color is the paper? White. The reason that we tend to think of it as yellow is that we're normally not looking straight at the sun, but slightly away from it, because the sun's whiteness is just too intense. And then you do see a little bit of a fringe of yellow lights that's scattered away from that. Nevertheless, at sunset then, the sunlight is going through a long slice, grazing incidence of the atmosphere. So there's more and more air there to scatter the light away. And so, looking towards the sun, the blue is gone out in every which direction, scattering into the air. And so it's removed from our line of sight. And what's left is the red, in the direction towards the sunset. So you notice that so much blue light is scattered away with that longer column of air that all you're left with is the red. All right, and that gets us up through the to where we will next start with lenses, which would be a nice chapter. Okay, by the way, with the Christiansen filter, it's actually a nice little project you can do. Different kinds of oils have different intersections with the index of refraction curves of glass at different wavelengths. And it's nice to experiment with these. Just make sure you don't wind up getting something that's the vapors from this are strong enough. All right.